Okay, good afternoon, everyone. Let us start the second keynote speech. Okay, I have the great pleasure of introducing our second keynote speaker of the conference, Professor Jun Tani. Professor Jun Tani is a professor at Okinawa Institute of Science and Technology Graduate University, OIST. Professor Tani is also a visiting professor of the Technical University of Munich. He's an author of Exploring Robotic Minds, Actions, Symbols, and Consciousness as Self-Organizing Dynamic Phenomena, published from Oxford University Press in 2016. As you can see from the book title, he is always working on the consciousness. Now, when I was a student, I strongly remember that he showed us the picture of complex and intertwined dynamical system. And he talks about the consciousness. And today I hope I can see the same picture of that one. And thanks. And actually recently the prediction paradigm is very popular in the brain modeling now. But since a long time ago, he was using prediction paradigm in the cognitive modeling. And now free energy principle is incorporated into his model. And he's proposing a new recurrent neural network with FEP. And then some of you might not like FEP, but this is a good place to have a healthy discussion. So I'm looking forward to listen to that kind of discussion. So please join me in welcoming Professor Jun Tani. The floor is yours. Please.
Yeah, thank you very much. Very kind welcome. And yeah, I'm very happy to be able to come back here and can provide you a talk in front of a great audience. Yeah, I'm very much enjoying it. Okay, so today, first I like to touch again the ghost in the machine idea. So then the ghost machine suggests no physical component. Is that? Oh, that's true. Okay, so ghost machine, can you hear me? Yes, okay. Ghost machine suggests no physical component accounting for the human experience. And okay, so Chalmers once considered a twin who are physically, cognitively, behaviorally identical, but one with phenomenal consciousness, and the other without phenomenal consciousness. So, but this becomes possible, logically possible, by assuming the dualist view, such as discussed by the René Descartes all the days, and which argues that phenomenal consciousness is a fundamental non-physical things or non-material things that is reducible to any other forms. So if the consciousness is non-material, non-physical things, then either with P consciousness or without P consciousness does not affect anything of physical cognitive behavior of the twin. So therefore, zombie without P consciousness, but cognitively, physically, cognitively, behaviorally identical to human becomes logically possible. So that is a point. So, however, alternative view has evolved through the history of philosophy and phenomenology. So I like to illustrate a little bit about this line, about this. So, and in my book, so Hiro kindly introduced, and yeah, I wrote a chapter 2 about a little bit about that kind of historical transition of the view of mind. And also, I have to say that recently, I very much inspired by this book, The History of Mind, Creation, Disappearance, written by the Kazeto Shimonishi. So this is very beautiful, and I wish everybody could read it. But however, it is published only in Japanese. So, but anyway, so I like to illustrate the transition of the view on mind in philosophy, and from the Descartes to Husserl to Heidegger and Merleau-Ponty to the Barrera. So that is Descartes. As I already explained, he is a dualist, and he considered that the mind is non-physical concrete substance that is capable of thought and consciousness independently of a physical world and the body. So dualist view. Then Husserl comes. The Husserl showed a little bit different. That is, the first Husserl famous for phenomenological reduction. So, and he emphasized the direct experience of the sensation of the object by suspending the a priori knowledge about the world. And then he talks about external world, object in the external world. So going out of the mind. So that is he says that the consciousness is always about something in the external world. So object in the world. So, and he emphasized the intentionality of consciousness toward object. So that's something like a relation to the object outside started. And Heidegger is a discipline of the Husserl. And he didn't talk so much about consciousness, but rather he emphasized what does it mean being in the world. So, and he wrote that the experience of the world is not primarily a matter of consciousness, but rather a practical and active engagement with the world. So, and then being in the world in terms of a relationship among the human and the object in the world, that is important for him. So this is a famous story about a carpenter hitting the nail. So, and then the carpenter used hammer hits the nail stuck in the piece of wood. So therefore you see the human and the object is kind of embedded in the relational structure. So that is being in the world in his thinking. So Merleau-Ponty, so I think everybody knows that he is famous for the embodiment. And I like this as what he writes about, that he writes that perception entails embodied action. The seeing is acting because of physical action to the object. Seeing changes the object. So then, because of the effects of a perception to the mind, seeing changes the subject. So therefore, subject and the object become inseparable entity by developing a reciprocal insertion and intervening of the one in the other. So maybe back to the carpenter thing that we have a kind of a top-down things and a bottom thing, and they are intervening each other. Therefore, subject and the object becomes inseparable entity. So that's Merleau-Ponty. And Francesco Varela, so that is there are many fans, a big fan in this community that I know. So I'm also a big fan of Francis Varela. And then, so he said that the consciousness is not a thing or substance that exists in the brain or mind, but rather it is a dynamical and embodied process enacted by the organization in the interaction with the world. And then, yeah, by reading this, you can see that, so what Varela is saying is very much inheriting the idea from Heidegger to Merleau-Ponty thing. So then, and he proposed in new discipline called neurophenomenology. So what he said is that we should study phenomenology, neuroscience, and nonlinear dynamical systems simultaneously. Then we can extract what it looks like of consciousness more explicitly through the mutual constraint among these three disciplines. So yeah, that's very great things, I think. Okay, so then by looking at from Descartes to the Varela, the very left side, so consciousness or mind is considered as very concrete things, non-physical, non-material things, and then irreducible and transcendent things. So, but on the other hand, the right side is going to be the more engagement with the environment, and the inaction is very important. Then we're going to have the interaction between brain, mind, body things, and then the and then mind or consciousness becomes a kind of ambiguous thing. So then we're going to put some people like Chalmers Tononi might be here, and many players in ALIFE, this community might, I think it's going to be the right side. And also I'm going to put myself in here because I have worked a relatively long time for the embodiment and consciousness things, enactment of the mind, and using by conducting robotics study. So therefore, so today I'd like to show you some of examples. And the first one is a very old one. That is, 1998, 25 years ago, I published the paper in a journal of constant study. Also, I presented this one in, if you remember, maybe you don't remember, but ECAR 97 Brighton, where I met many people, including Eamon Harvey, Phil Husband, and Neil Sess, and those people. Anyway, and this is about mobile robot navigation task. So this is a mobile robot and having a vision, and it's moving around this kind of environment, relatively simple environment, by following the wall, so attending to the wall. But there is something like a landmark and a colored landmark, and then we have a 3 in a corner type landmark. So then there are actually 5 landmarks if the robot go around this environment. So the task of the robot is the robot has to incrementally or dynamically run to predict the next landmark it will encounter along with their visual image and direction and the timing. So that's the robot has to do. So then in order to do that, I consider this kind of the architecture, the higher level, lower level we have, and the lower level in something what pathway, there is a Hopfield network. The Hopfield network runs to memorize multiple visual landmark image, the colored image things using camera. And the other side is where this coherent type network runs about the direction and the timing of a landmark encountering. And the higher level, we have recurrent network. That one runs to predict what, where, and when about landmark encountering in a relatively abstract manner and sending bias signal to the Hopfield network and the coherent network so as to generating the image of the landmark. And then we have bottom-up sensation coming. Then if there is error between prediction, then that error is averaged over the recent time steps and getting some kind of predictability, how much robot can predict predictability. That one is used to arbitrate between the top-down and the bottom-up interaction. That means that when the predictability is high, more high confidence for the top-down prediction. So in that case, is that the robot tends to attend the object only shortly because Hopfield network is soon converge by using the adequate top-down bias. On the other hand, and the predictability becomes low, confidence becomes low. So therefore, in that case, is that the robot have to look at a longer time for the object because the Hopfield network needs more time to converge because top-down things cannot be trusted so much. So something like this kind of the arbitrated top-down, bottom-up interaction goes on, depends on the situation, and the robot has to learn about encountering of the landmark. So then this is something like a so robot is now looking around, attending to the wall, and then colliding avoiding collision and moving smoothly. And now it's predicting this landmark things. Landmark is coming and predicting, and then robot is in a good timing. It's now looking at, so that's predicting when it comes and looking. Okay, so the good timing and robot is attending it. So now and the interaction and the Hopfield network soon converge because prediction is very good. And the next landmark coming, predicting again this one and the good timing and the Hopfield network converges to the matching. So that kind of thing. So this is a result of time development of the system during the successive learning while exploring. So this one is a prediction error. This is neural dynamics, recurrent neural network dynamics in terms of bifurcation diagram like things, but the internal state representing. So this is something like a 15, like a event steps, landmark encountering 15 landmarks, 30 landmarks, something like that. So then as time goes by, so then initially, of course, prediction error is very large. However, it goes once, it looks like converging, but it goes up, and it's almost converging, but again, it's peaks up and converging and peaks up. That kind of thing is repeated. So then that is, for example, this is a predictable phase of the error is minimizing this part. Then first we see that there is this state 1, 2, 3, 4, 5. So 5 line we can see that is actually representing the period of 5 limit cycle. That is 5 is important because there is 5 random marks. So therefore moving around 5 times. So then there is 5 things in the sequence, right? But so then there is the 5 you can see here also. You can see here also. And when the predictable robot becomes very predictable, trajectory becomes very smooth. So that is one thing. And however, in unpredictable phase, the error pick up, and then you see that no more period of 5, but rather chaotic dynamics often appears. So no non-periodic anymore, and it looks like a robot is confusing. And in this case, the trajectory becomes very much winding. So, and the important thing is that there is we see the spontaneous shift between predictable steady phase and unpredictable unsteady phase. That is spontaneously shifts. So, and if we do another trial, then we see that something similar appeared, like a period of 5, and the chaos things, those things are intermittently switching. So that's we often see. So why did it happen? That is what we found is that some kind of a circular causality developed in the enactment loop. So that is sometimes prediction error goes wrong. And then because of the conflict between the top-down prediction, bad prediction, and the bottom-up sensation, so perception could take longer time. As I told you that the Hopfield network takes longer time to converge by having an inadequate top-down bias. So then prolonged perception for the altered attended visual landmark could make wall following very unstable because the robot is looking at a lot of the time only for the visual object from left side, but not looking at the right side of the wall. So therefore, nearly sometimes hitting something. That's why trajectory becomes unstable. So the instability of maneuvering could cause the next landmark to be overlooked. Therefore, sometimes robot CD only 4 times in one run, sometimes 6 times once run. So therefore, it's a robot sequence running confused. Then and kind of a chaotic attractor appears. Then that makes, then this loops back. So then the prediction goes wrong. So it's kind of circular causality goes wrong. So then, yeah, and this part might be something analogous to the internal observer. That's all the days that Gunji-san talked about, but I cannot go so much detail. So, and what we found is that a sort of indeterminacy develops because of the circular, this type of circular causality. So then in this, there are 2 types of vector flow coexist. One for the convergence by trying to kind of goal direct efforts, try to minimize every error to minimizing. That is one, try to converge. The other is the divergence due to the circular causality. So by enactment, that is even though we want to minimize the error, however, something spontaneous perturbation and emerge, the divergence things, that is, we cannot avoid it. So in case of the embodiment. So therefore, we're going to have the unsteady phase and steady phase iterate intermittently. So then now I'd like to explain the structure of consciousness that I'm thinking about. The first, we have top-down things, the bottom things, and then sometimes non-conflictive, sometimes conflictive interaction goes on. So then we're going to have the predictable phase and unpredictable phase in the intermittently switch. Then look at this predictable phase. I'm now going back to the Heidegger. So, and he said that when everything goes smoothly, automatically in a hammering, the carpenter, hammer, and the nail constitute wholeness. They are not separated. Therefore, everything goes smoothly and automatically. Therefore, we are unconscious about self, unconscious about object. However, when something goes wrong with carpenter's hammering, then independent existence of the subject, carpenter, and the object, hammer, is noticed. So that is at the time of the breakdown, we first time notice independent existence of self and the object. So we become conscious about self and the object at this moment. So that is my interpretation by making correspondence, my experimental results to what Heidegger wrote about. Okay, so then again, structure of consciousness. So what we observe is some kind of emergent structure. So unpredictable phase and predictable phase intermittently transit. So, and because of the sort of indeterminacy by the circular causality. So then what I think, in order to understand structure of consciousness, it's not enough to only look at consciousness, but we have to pin down, understand the mechanism of how consciousness appeared from unconsciousness. How the consciousness state goes in a decay into the unconsciousness. This kind of dynamical mechanism have to be understood. So then if we can understand, then we can make correspondence to what William James used to talk about, stream of the consciousness. He talks about, that is, he said that it's like a bird's life. So alternation of the flights, that is a transition part. And the perching, that is staying the same phase. So that kind of things that intermittently repeat. That is stream of consciousness, according to the William James. Okay. After this study, my group went to the exploring some analogous model to the predicoding and active inference. And then, but those days, we didn't know the terminology like a predicoding, active inference 20 years ago. So, okay, but first, yeah, so predicoding is a theory for the perception. The basic idea is minimizing error between top-down sensory prediction and its bottom-up, bottom-up outcome by inferring the latent state. So that's kind of generative model we have. So then by inferring the latent state to minimizing prediction error, if you can achieve it, then perception achieved. Then active inference is, on the other hand, active inference is a theory for action generation. In this case, minimizing prediction or minimize desired sensory state and the current sensation by changing the sensory inputs by adequately acting on the environment. So this is active inference. However, important thing is that these two are not separated process. As action and perception make a loop through the environment. So that is, I think that we know that. So, and then we have worked on some hierarchical recurrent neural network relatively long time and changing the many parts as time goes by. So, but I like to show that kind of thing. But this one is actually 2008 version and developed with Yamashita-san. Probably he's here around somewhere. But anyway, so that the idea is that the higher level is slowly operated. That time constant is large of a neural activation dynamic equation. The fast and the lower level is fast dynamics. So then time constant is set to small. Then we have maybe this part is associative layer or associative cortex or prefrontal, and spanning to the branch, we have one is a proprioception for more movement related. And the other is the vision things. And we may have a kind of the intention for acting, particular intention for acting the environment associated with predicted image about perception. That is how the body posture is going to change in time. The other is exteroception or vision, how the visual image change in time. That kind of prediction is simultaneously made. And then this predicting next proprioception state. Proprioception means that the predicting next target joint angle in the case of the robot. Then that target joint angle is fed into the PID controller, and the PID controller generates the necessary motor torque to achieve the target. Then, acting on the environment, the state change appears. Then we're going to have a new sensation about the proprioception and the vision thing. So whenever you predict, we're going to get at least minimum level of the error, right? So then that minimum level of the error, so that error is going to bottom up. Then we're going to have, if there is an error, that means that we have an internal conflict between top down and bottom up in each layer. And we have the output part of the error. And we have to minimize these things. So conflicts, the error. So by changing updating the intention, or maybe simultaneously by acting on the environment. So therefore, we have the one thing is that the mind state is changed. And the other is that the world state changes for minimizing the prediction error. Then how they are changed, that actually the business of the interaction, top-down, bottom-up interaction. This is in many cases very much nonlinear and very much dense interaction. So therefore, we do the robotic experiments to look at how it looks like. So, however, there is a problem. So recurrent neural network model we employ is a deterministic model. So therefore, some people say that it's difficult to predict some probabilistic interaction, probabilistic phenomena. Then, but deterministic dynamical system person in camp people like me often say that, oh, but whatever probabilistic phenomena, probabilistic sequence can be imitated by developing a deterministic chaos. But formal probabilistic modeling people say that no, we should better to use formal model like a hidden Markov model. So there are dichotomy between two sides, right? So deterministic modeling and the other probabilistic modeling. And are there any way to bridge the gap between these two? So that is my question. And then I thought that, when I first time know about Princeton and the free energy principle might be the way to resolve this dichotomy. Especially, I like the idea of the precision structure. So that is a confidence of top-down prediction. That is something analogous to what I have done in predictability things. So, and also, if we use free energy in a more continuous domain, and then we don't, assume probabilistic things. So, no. But it starts from a continuous stochastic dynamical system, and without notion of the probability, the notion of probability may develop. So that is, so I'm very much interested in the phenomenological origin of probability, how human people feel like a probabilistic or uncertain of those things. So, yeah. So in this purpose, so we developed something called PVRNN, my student Reza, and that's a recurrent neural network model based on the free energy principle. So then that model is minimizing free energy in case of the learning or action generation. And although I cannot go the detail of this equation, but the important thing that there is free energy is one thing is that we want to minimize prediction error. That's the maximum accuracy term plus complexity term minimizing. So what is this complexity term? Complexity terms are actually conflict between top-down, bottom-up. So, but more precisely say, that's making the the divergence, KL divergence between approximate posterior and the prior minimized. So in the probabilistic domain. So then we are putting something like a W. So that is we call meta prior. We're going to explain that one later. So and the weighting of these things. So then now look at in a graphical model of PVRN. So PVRN, we have a probabilistic latent variable Z. And then that one, and actually this time step goes like this one. Okay? So then we have a prior and posterior, that's change in time. So prior change in time comes from the idea of a sequence Gaussian prior originally proposed by the Chung. So I use that idea. Then, so we have the posterior, how posterior obtained, that is, I'm going to explain later. However, anyway, this posterior probability distribution and the noise sampled, the real value comes. That one is mapped to the deterministic latent variable D1, D2, D3. So that is each step, so mapped to this one. And this one is further mapped to the sensory sequence prediction or deconstruction. So X1, X2, X3 things. Then if this is a learning process, we have already observed observation of sensory sequence like this one, that we want to minimize the deconstruction error here. In order to minimize the error is backpropagate, that go up the error and also backpropagate through time. And what we do is that the error signals coming to this posterior and updating posterior in the direction of minimizing prediction error. However, important things, posterior cannot be arbitrarily manipulated because prior and posterior KL divergence have to be minimized. That is, two should be something similar. That is better. So that is the complexity term. And also we have to minimize prediction error. So then if both are satisfied, free energy is minimized, then learning or action generation goes very good. So in case of the learning, the minimizing free energy is actually, we're going to optimize synaptic weights of this recurrent network. The also posterior value, each step is an inferred. So that is we're going to get. So about this meta prior things, we're going to, if we change the W, so learning results, action results going to be very different. That's part I'm going to especially first look at how W affects the learning. So that I'm going to show. Through the first simple experiment, before going to the robotic experiment, we did a simple experiment like learning with the probabilistic finite state machine, very simple. So we consider this kind of a target probabilistic finite state machine. After 1, 0, this is deterministic. Then 1 is 70%, 0 is 30%. And this probabilistic finite state machine generates sequence like 1, 0, 1, 1, 0, 0. So that's kind of sequence generated. This part is probabilistic. So then this PVRN have to learn to regenerate this kind of thing. So, and then we did training the network using large W and small w to compare. So then this is the result. In the case of the large W, W is 0.1, and this is W 0.025. In case of W equals 0.1, so we look at this is the output of a generator. So 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. So it looks like, following this one almost. So output is okay. Then looking at the prior sigma is this one. Each step we have prior sigma. Then that one looks very much 0, almost 0. Then, so that means that there is no stochasticity, probability thing, zero stochasticity almost. Then we looked at the Lyapunov exponent and it's positive. That means that this probabilistic sequence generated by developing deterministic chaos in case of the W is large. when the W becomes very small, the internal representation is different. First output is again something similar like this one. And then, but if you look at the latent state, so in the sigma standard deviation, and the small, this is when you go here, small, then at this branching node, then STD, standard deviation goes up. So that is always so. So that means that this branching is generated by using noise sampling, much bigger noise sampling, right? So therefore, this is a stochastic dynamic. In case of W is very small. So what we see is something like we are observing, network observing same seemingly probabilistic sequence, but if you set W very large, what we got is high precision prior, almost 0 sigma. That means deterministic dynamics. And on the other hand, if we set the W very small, low precision prior, large sigma, that means the probabilistic dynamics emerge. So that is something important. The next question is, which aspects in the human or animals embodied cognition can be accounted by this W-dependent structural development shown in the previous simulation? So my students, Nadine and myself, worked on a robot-robot imitative interaction experiment and found some kind of the answer for this question. So what Nadine did is something called synchronized imitative interaction based on learning. What she did is that, so we have 2 robots, but each robot is pre-trained to predict sequence of primitive pattern that follow a specific probabilistic finite state machine. So that is something like this one. So robot 1, robot 2. So robot 1 is kind of the process is that it is each robot is independently pre-trained. So that's not the mutual learning, not yet, but so the independent training. In that case, robot 1 facing in the mirror and looking at my own movement and runs to generate A pattern first, then followed by C pattern 80%, but sometimes the B 20%, and back to the A pattern. This is repeating, right? And because of mirror image, so robot can associate not only joint angle movement, but also visual images associated like this one. But this case, visual is very simplified. And then robot 2, almost similar structure. So A, but after that, only 20% of the C. The 80% is B. So therefore, preference is different after A. This robot 1 wants to generate more C. Robot 2 wants to generate more about B. So then that is going to be the, in case of synchronized imitative interaction, it's going to be conflictive after generating A. So that is, so we intentionally, I think, this kind of task setting. So then training is repeated with setting different W, many different combinations. Robot 1 large W, robot 2 small, both are small, something like that. So then we did experiments. So then after the learning, 2 robots interact by generating own movement pattern while perceiving pattern generated by the other. So that is coupling. I'm going to show more about it. So robot 1, robot 2 we have. The robot 1 is a prior generation, the prediction, and that one is going to predict visual image and the next time step, and also the joint angle of the next time step. That one fed into the PID controller, the robot actually moves. And then that one movement can be observed, can be predicted by the robot 2. And the robot 2 also generated own movement pattern by the prior generation. Then if you have the error, so this robot is predicting not own movement, but other, but because this is not mirror. So looking at the other robot. And if there is error is back propagate bottom up and changing and updating approximate posterior for the direction of minimizing free energy. At the same time, and this robot also does the update of approximate posterior. So therefore, this case, the coupling is kind of predicting each other. The error is feedback and influencing the latent state for minimizing the free energy state. That is coupling. So then I'm going to show you a little bit more about hierarchical network of PVRN. So higher level is slow dynamics. And then we have an intermediate level and fast dynamics level. And this is the prediction of our proprioception vision things. And then it's going to be, then this is time step goes like this. This is now. This is the past. But the network always try to reconstruct by generating top-down pathway, the forward pathway, and then the reconstructing the visual perceptive image, and against the observed one. So this is the observed one. If there is the error, then again that back propagate and updating posterior for minimizing the free energy. This is necessary in order to make latent state straight to the past sensory sequence. So whenever new sensation comes, the latent variable in a very far away past might be also changing. That's reflecting the past or post-prediction about the past. That is very important. Dynamically changing my understanding of the past while predicting for future. So once each sensory motor step, free energy minimized, well shaded, then predicting for the future. So that is, then after good, then this is iterated. Then next sensory motor step proceeding, then we do the same thing. So that's actually costs a lot of computation. Okay, so then specific question is that what sorts of interaction can emerge depending on the setting of the W. So then we're going to look at robotic experiments. So robotic experiments, I'm going to show. So first, this robot one set with small W. This robot set with large W. The training is done. And now it's going to interact with each other. So you see that the first, so now you see that this side of the robot, this is predicting future. This is the past. Now is around here. The prediction is very unstable, but this robot set with a high W, predicting future very good. So A, then B, A, and B, and B, but this one is sometimes broken. So that difference. Now is that, okay. Now robot is synchronized with the A. That is easy because share. Then this robot over this one is wants to do the B, right? But this robot is following after because this robot is preferring C, reluctantly doing. So A, then high W robot is reading, then B. This guy is following reluctantly, something like that we see. So when we set both robot large W, then first we see that in a both robot predicting future is very, very stable. But this guy is doing the C, this robot is doing the B, ignoring each other. So they are doing own preferred one, regardless of what others are doing. So that we see. So very stable. When we set both robot W very small, then what we see is very, very stochastic, both sides. But A is okay because shared pattern. But so then now it's kind of confusing a little bit. And now it looks at synchronized with C. So he's reading C. And now go back to the A. Sometimes it switches to the synchronized with B. So this unstable phase, we sometimes see the spontaneous switching. So like, turn taking like things we observe. So then this is kind of a neural dynamics. So when robot one set with small W, robot two set with large W. So then you see that this is pattern C, the A, B, A. So that is almost synchronized. Then I like you to focus on this one, yellow and black one. So that one, this is the probabilistic latent variable of the lower level. Then you see sometimes difficult to say, but it's a divergence. You see divergence often. So in case of W set small w, in a posterior and prior is sometimes diverge. But on the other hand, when you set W 3.4, posterior and prior is very close. So that is one observation. And the other is that maybe related time scale thing. That is, this is a higher level thing. This one is whenever it generates A, coming back to the A, it goes up. And it goes up. So that is kind of more abstract sequences encoded in. The same for the robot 2. So you see something similar things coming. Okay. So then now I'm coming to like, so in this robot is trained with large W, and then prior becomes very high precision prior comes with a very small standard deviation. That's why posterior is attracted by the prior, right? On the other hand, now weak and W set with very small and training, the prior will have a low precision and with a very large standard deviation. That's why posterior is attracted by sensation. That is why this robot is following more sensation. That is following the other. So this robot is likely afforded by sensation. However, this robot is following own intention regardless of sensory input. That's why this robot becomes leader. This robot becomes follower. So that kind of W thing is this kind of things comes, the W setting. So then, but up to now, in our study, W was set in the training phase as a fixed value, and it's continued to be fixed during action generation. So that's why, once you train to the positive robot, it's going to be always positive. And once trained on a passive robot, it's always passive. But the question could happen, can we arbitrate top-down, bottom-up process of an agent by shifting W during the interaction phase? Yes. And then can the same individual, that means that can the same individual become sometime active or passive by changing W depending on the situation? And my student Wataru showed, yes, we can do that. So then based on that idea, and my another student, Hiroki, performed human-robot interaction through kinesthesis by focusing on the force. So, and the humanoid robot of this one is trained to probabilistically switching like a pattern B to the D or something like this one by following this probabilistic finite state machine. After the training, the Hiroki physically interacts with the robot by grasping his hand. Then, and then try to induce the untrained transition, like from B generating suddenly to C or something like that. Then looking at what kind of reaction force he will feel, what kind of reaction force comes. And that's depending on the value of W set during the interaction. So this is a video, right? So now robot generating the B pattern or something. So then, yeah, this is predicting future. This is the past. And now he induces. So now you see that torque goes up and the KL divergence becomes large. The conflict comes. So he continues something like that. But this case is that W is very small. Switching is very easy. So then what he found is that the large W case hard to change total movement pattern encountering with a large reaction force because of a very strong intentionality of robot. Robot doesn't want to be changed. Right? But in the case of the small W, easy to change the pattern encountering only with small reaction force because the intentionality of the robot is low. So then that means that the human can feel intention of the robot. What he wants to do, he might even I ask the robot to do this way, the robot no, robot, go this way. So I can feel the intention of robot, what he want to do. So that is many future applications like a tutoring a robot and a hand by hand or something like that. And then, so that is something important thing that a top-down prior is now translated to the reaction force. So I think this kind of a bodily interaction very important for the human-robot interaction things. Before introducing fancy, language communication, I think. First, we have to do like this kind of things, I think. Like focus more on the force or something like that. So then, now I'm finally coming to the almost the end point. So, and today I have shown that the arbitrating between top-down intention and the bottom-up perception, depending on W. So that is a large W cases that high precision prior. So then that is cases that strong top-down. Therefore, subjective mind extend into the environment, external environment. On the other hand, if you set small W, low precision prior, and that's a strong bottom up. So therefore, external environment extends into the subjective mind by the sensory affordance. So then now we are studying, not yet accomplished, but is try to do the autonomous adaptation of W. The previous experiment, the human set W, the change, and then look at how it's going to be. But autonomously W, changing W for the better performance. So we are working on. So then if it is successful, like autonomous adaptation of the W, depends on the situation, then what we will see is that probably these two phases of mind extended to the environment is one side. The other is that the environment extended to the mind. These two things is automatically switch and associated with the autonomous change of the W. Then this might be something like the boundary between a subjective mind and the objective world floats autonomously. Then this is analogous to the idea ambiguity of the mind, which discussed by Merleau-Ponty, also Barrera. They talk like mind is floating, not static thing, floating between the two extremes of subjectivity and objectivity. That's written in the embodied mind of the Barrera by referring to the Merleau-Ponty. Okay, so then finally, final slide. So which one? So I come back to this one, dualism things and inductivism. So dualism things that, is consciousness as a non-material things and the non-physical things, and then the consciousness treated as a very transcendent things. On the other hand, inductivism, that is everything kind of about interaction dynamics among the body, brain, and the body things. And then resultant dynamics always go to the, probably it goes to the ambiguous things. So two things are very different. So then I back to the Kazeto Shimonishi. So he says that the mind or consciousness does not exist naturally, but it is something human invented as a metaphor based on the historical content of their time. That is very interesting. And then I very much sympathize with what he's saying. So therefore, I also cannot deny either invention as a metaphor of consciousness. So both are logically possible, I think. So then, especially if you think that consciousness or mind is non-material things, then this is possible. If you think about the consciousness as a material things and physical things, all the interaction dynamics starts amongst mind, body, and the environment. So then this kind of things becomes possible. So it's kind of ambiguous state of the mind becomes possible. So both are possible, I think. However, I myself believing very much like, even consciousness, those things are still material things, the physical things. Therefore, I'm staying this right side one. Okay, thank you very much.